While the world is currently focused on one particular kind of virus, I'm sure you know which one, let's take our minds off that and talk about a different kind of virus, the kind that's a threat perhaps as old as modern computing itself. Or is it? Well, we have to define what a virus is first. According to Wikipedia, a computer virus is a type of computer program that, when executed, replicates itself by modifying other computer programs and inserting its own code. Virus is actually a type of malware. Malware being a combination, or a portman, however you say that, of the words malicious and software. Malware is defined by Wikipedia as any software intentionally designed to cause damage to a computer, server, client, or computer network. There are many types of malware, such as Trojans, computer worms, spyware, and ransomware, all with different types of specific goals. But as long as the intention of a computer program is to cause damage maliciously as opposed to unintentionally, like via software bug or through misuse by a user, like with the infamous Disk Destroyer program on Linux, erasing many precious files with zeros and random data through the years, then it is malware. A program may also be considered malware if it does an action the user did not intend to do, or does something without their consent. A good example is the Sony music copyright protection included on some of their CDs, which included a driver that allowed a piece of software to perform actions with elevated privileges, bypassing the user and without the user's knowledge. An example of that is Windows 10 with telemetry and updates. Though I guess if we're being fair, they do let you know in the end user license agreement, so well, a computer virus is perhaps the most commonly known type of malware, so I will focus on that for this video. A computer virus is actually quite an old concept. The Creeper is widely accepted as the first computer virus. In 1971, Bob Thomas, working at the time at BBN Technologies, an American research and development company based in Massachusetts, wrote an experimental self-replicating program known as the Creeper system to test mathematician John von Neumann's theory of self-replicating automata, an article published in 1966 about a concept of specialized computers that could build copies of themselves. The Creeper infected PDP-10 computers running the 10X operating system using ARPANET, which was one of the first TCP/IP networks in the world, long before the internet, to facilitate its spread. It was later stopped by the first antivirus software, the Reaper. The Creeper did not cause any damage per se, so while it's a computer virus, it's not technically malware. All it did was display text and, well, move. Although one could argue that moving itself from computer to computer without the users knowing explicitly and printing text without their explicit consent could be considered malicious. But the important part is, considering the potential of such a program, especially the later revision created by Ray Tomlinson, which was designed to actually copy itself rather than move itself from one computer to computer, it's no surprise that it became quickly associated with the concept of malicious use of software. And so, the computer virus was one of the first types of malware to come into existence. Although the term itself didn't exist until 1986, when Fred Cohen, a PhD in computer science, coined the term in his thesis. As for malware, it's a bit more difficult to pinpoint its origins. Technically, any program written to sabotage or harm the equipment or anything in connection with the equipment with malicious intent could be considered malware, so there may be some we're simply not aware of. Humans do love to destroy things, so I wouldn't discount the possibility of some disgruntled coder back then writing code on, punch cards that make the machines jam on purpose. I guess we may never really know. As far as I know, this virus is one of the first types of malware to come into existence. But that's some historical context for you. By the way, if you were such a person that you wrote code on an ancient computer that, created some troubles or were involved with computer equipment that could be best described with the Beastie Boys song Sabotage, let me know in the comments, as long as, you know, the statute of limitations expired wherever you live, I suppose. Well, anyway, let's jump ahead a bit to the 8-bit home computer era in the 80s. One of perhaps the most famous examples of harmful bits of code, let's put it that way, from that era is the poke of death, or the killer poke. A singular command that could kill your computer and be tucked away in any program you run. Commonly, when people use the term, they're referring to a Commodore PET poke command that relied on the architecture of some of the models featuring video rasterization circuitry that could destroy the integrated CRT monitor that came with the computer with one single poke command. A previously harmless command on old PETs that made the machines able to display text on the screen faster and could irreparably damage the CRT. Well, or so it's commonly believed. In April 2020, Adrian's Digital Basement and Tech Tangents, great channels by the way, made a video disproving the fact that it can indeed kill a Commodore PET, which you should go watch if you want to find out the technicals of how it worked. Albeit, as a post on 6502.org states, it's theoretically possible to fry the screen electronics via a different method. So, stay safe out there when running unknown software on your beloved pet. Get it? I'd also say, like, keep your pets safe. Or do you think that would be funnier? Let me know. But let's get away from puns of death and get back to pokes of death, which aren't exclusive just for the pet. If you remember from my other videos, or perhaps know just as a Commodore 64 user, the 5¼ inch 1541 disk drive used with the C64 was actually kind of its whole own computer, one that ran on the same CPU as the PET. This 6502 processor would be used to manage the drive mechanism and would handle the low-level data accessing and simply send it back to the C64 to display or load or whatever the user wants to do with it. However, it's possible to send a command directly to the drive so it can access its I/O registers. Memory write was the Commodore DOS, which the drive internally used, equivalent of the basic poke command. By using basic to direct a special command to the drive, one could access its registers for controlling the drive motor. And due to a lack of what's known as sanity checking in the motor hardware, basically making sure that things are behaving as they should be, if the drive was told to keep moving despite reaching the first or last track of the disk, the drive head would be knocking against the mechanical stop, which eventually would bring the drive out of alignment, since it would be essentially bashing against another piece of metal. A bit more like the PET was another 8-bit computer with the potential for damaging video hardware. It was the TRS-80 Model 3, which had the ability to switch between a 32-character wide and a 64-character wide display, which triggered a relay in the video circuitry to make the switch. This could be done by writing to a specific control register. If a program by accident or on purpose used this command repeatedly and very quickly, it could permanently damage the hardware. While not a singular poke of death, this could very well be still embedded into a program designed to destroy equipment and disguised as just any other odd program. Which is why I think what makes pokes so particularly scary. On the Game Boy, which is an 8-bit machine, a special poke to the LCD control register, FF40, in particular bit 7, can be used to turn off the Game Boy's LCD screen, doing which, outside of its vertical blanking interval, can allegedly damage the hardware, an issue that was so prominent Nintendo reportedly rejected any games that did not follow the rule of only turning off the screen during the vertical blanking interval. Something that affected a whole number of computers, was less destructive yet still possibly damaged, was code that interacted directly, intentionally or maliciously or not, with a cassette tape relay used in computers like the TRS-80, the IBM PC, PC Junior, MSX, Amstrad CPC, as well as the BBC Micro. Interacting with this relay would reduce its longevity, and it's not far-fetched to see the code that would intentionally mess with it to destroy other people's hardware. Or maybe not. Maybe people were just nice back then. A program containing any of these would most certainly constitute malware, although no record of any incidents involving programs like that exist, or at least none that I could find. But watch out, you could always be the first. Or the second, which is even worse, because then you don't even get to really talk about it as much. But if you know of any such incidents, please do let me know. I'd love to hear about them. I think it'd be especially dangerous now, considering those machines aren't made anymore, and functional hardware will only become more scarce over time. But at the same time now, with the internet, malicious software that destroys your prized retro computer is unlikely to spread too far before somebody finds out, either destructively or hopefully by looking through the code. Let's dial it down a little bit. Equipment destroying is all fun games. Well, actually, it's terrible. But on the subject of fun and games, there were also more harmless one-liners, things that could be removed with just the restart of the computer, annoyances, and things meant to just scare people. While not malware, those annoyances could be considered to have a little bit of malicious intent, sort of like a mean-spirited prank, but it's not really malware in the traditional sense, as it doesn't harm anything or anyone, nor destroy anything. It's worth mentioning some of these, especially on the C64. My favorite personally is printing text, a simple loop to print some kind of text forever using a go-to statement. But someone could easily stop it from doing so by pressing the run stop key, breaking the execution. However, with a simple poke statement, we can block the use of run stop so the message will indeed go on printing forever, at least until the person turns the computer on and off. Simple, but I imagine pretty effective in an era where computers weren't so intertwined into our lives, and the average department store employee would probably at best know to just turn it on and off again. We could also turn off the keyboard entirely with poke 649, 10. Somewhat more malicious is the command that makes all keys repeat. Poke 650, 128, and just leave the C64 as it is. Someone who didn't know any better would have thought the keyboard was broken, perhaps. But that's all pranks in play. I just thought it would be fun to mention these because there are so many of these, and I'd imagine if I were alive back then, I would probably be one of those kids who would love to play pranks like that. But what about the real meat of this deal? I said earlier in the video that we're going to be focusing on viruses, and so far I've kind of been dancing around the topic. Well, let's take a look at some 8-bit viruses now. One of the first viruses to make the rounds on 8-bit computers was for the Apple II series of computers. So much for Apple doesn't have malware, eh? Well, the Elk Cloner was written by Richard Skrenta while he was in high school as a joke. Usually the virus would attack the boot sector of the Apple DOS operating system, which, as you might have figured out already, is an Apple version of DOS that was supplied back with Apple computers back when this virus made the rounds in good old 1982. Its payload, the code that executes on the computer, made the user's screen blank and displayed the following poem about the virus. Okay. Surprisingly, it did not cause any other harm of any kind, so it's not really malware as far as I'm concerned, although one side effect of its spreading mechanism was that non-standard Apple DOS disks had their custom tracks overwritten, which, could be annoying, to say the least. See, the virus would spread by overwriting any uninfected floppy drives inserted into the computer with the current Apple DOS loaded into RAM along with the virus code. Since back then, DOS would get loaded into RAM rather than be stored on a hard drive like in later computers and loaded from a boot disk, these boot disks is how the virus spread, overwriting the DOS boot section with an infected version. And of course, if this infected disk was now used to boot, the virus would get loaded into the computer's RAM, the booting computer's RAM, and then any other disks inserted after that would get overwritten with the DOS and the virus. Upon the 50th boot process, it would trigger the payload and display the poem, annoying the user. If your floppy disk wasn't actually an Apple DOS boot disk, it would not check for this and still overwrite the floppy with the boot sector code, thus the effect of it damaging disks on which those tracks were used for something else. One particularly interesting aspect of this virus is Richard Skrenta himself. According to legend, he would often make these kind of pranks on his friends while trading pirated software disks in a computer club in Pittsburgh, which allegedly distrusted him because of it. A distrust of pirated software today is still a thing people have, rightfully so. But nonetheless, people wanted software for free badly enough that, again, even back then, allegedly, the virus reached as far as Baltimore, Maryland. Some things truly never change, eh? Another virus that affected 8-bit machines, but not just those, is the brain virus, as it's most commonly known anyway. It was originally a tracking program for illicit copies of a heart monitoring software for the IBM PC, a way to target copyright infringement by messing with those who dared to pirate the software. Making its way out of Pakistan, it infected the boot sectors of floppies in both the UK and the US. It dealt no real damage, but instead simply stored a message viewable by accessing the raw boot sector data. It also slowed down disk access because of the way it worked. It stored itself in the boot sector of the disk while backing up the original boot sector elsewhere. Thus, anytime it was accessed, it would be redirected to the functional old boot sector rather than the boot sector that was written with the message, allegedly making some disks unusable. It also changed the disk label to the brain name and the copyright symbol, likely chosen because the two brothers who wrote the virus originally owned a store called Brain Computer Services. Since it would infect any floppy disk, one could say that while it's not destructive in nature, it does perform actions without the user's knowledge and did far more than just track illegal copies of one program as it was allegedly supposed to, spreading all over the place, causing a real ruckus back then. So I'd say it's pretty much malware. This is a pretty well-known virus, but let's talk about something a little more obscure and something that you've all been waiting for. Commodore 64 virus. Hell yeah. The first computer virus for the C64, as far as we know anyway, was the BHP virus. No relation to the programming language PHP, although that one can certainly be considered quite a virus in its own right. The piece of code was written in 6510 processor assembly, called by a line of basic code, much like most assembly C64 programs of its day. Usually one would load and run a program without knowing that it's the virus. Upon its run, it would store itself into the RAM of the computer and hook into load and save routines, so it can copy itself to other files on the disk. It would occasionally display some text as well. That's pretty much it. Here's how it works. When an infected host program is run and the virus code is executed, it will, like I stated previously, store itself into RAM, specifically into the blocks of memory occupied by the input-output devices such as a disk drive. For the uninitiated, very basically, the RAM on the computer is memory that the CPU can address with specific registers like D000 in hexadecimal format. And that's how it stores and saves information to RAM, by writing to and reading from these registers. These registers belong on a memory map. This is a range of addresses which the CPU can address, which includes RAM, but also things like the ROM chips where the kernel and the routines within are stored, or the ROM chip where the basic interpreter is stored. It also includes things like I/O devices, which means that the CPU can access these devices like a set of memory addresses same as RAM, to be written to and read from. This is how a CPU can access things like the video processor inside the computer to draw information on the screen, or the sound interface device. If you remember from my C64 programming video, we used a poke statement to write a specific byte to the SID chip registers that made it beep. We effectively just wrote a byte to one of the registers available to the CPU on the memory map. That's how it interfaces. So peripheral devices like disk drives on the C64 also have the same situation where they can be addressed by specific addresses in memory. The same general principle is still true in computers to this day. Open Device Manager in Windows 10 and click View and click Resources by Type. You'll see memory and I/O mapped to specific address ranges. With me so far? Okay. All is not so simple, as there can be more memory addresses that need to be available than the maximum amount of memory addressable by the CPU. For this, a technique known as bank switching is often used on 8-bit computers. The addressable memory space by a CPU determines whether it's 8-bit, 16-bit, and 32-bit, and so on, with each increase using more bytes to describe and address the virtual memory address. By today's standards, even the measly 4 GB that are addressable by a 32-bit CPU are pretty pathetic. So the 64 kilobytes addressable by an 8-bit CPU is understandably quite limiting. To make things worse, in modern system, I/O devices have a separate address space, but the C64 and other 8-bit computers did not have such luxury, and so everything was usually on the same memory map. To allow the full 64 kilobytes to be usable, bank switching is used. Special I/O pins on the CPU can talk to the PLA chip, which can send signals that control which chip is connected to the CPU, effectively to select a specific bank of memory addresses to be addressable by the CPU, depending on the situation. The Commodore 64 uses this to make certain parts of memory addresses that belong to the RAM to be switched over for the addresses that belong to the I/O devices instead, but can be switched out back to RAM based on what's needed. That's how C64 cartridges can add RAM to the C64. The amount the CPU sees and can address is never increased, but simply switches in and out at the same address spaces with the different physical chips available for data storage. Some of these addresses are occupied by the I/O devices, such as disk drives. All of this is to say that it provided quite a fancy hiding spot, possibly the most ingenious part of the virus, since the virus would copy its code to RAM address space that was usually occupied by the I/O devices, and so would not be normally visible to the user. It would then actually restore the host program the virus was inside of in the first place to how it was originally, to ensure it could continue execution as normal. Meanwhile, the virus, after making sure it wasn't already running, would copy some of its code to a non-banked area of addressable memory and hook in the file save and load and reset vectors along with some others, which meant that whenever the user would attempt to execute any of these, such as saving a file or loading a file from disk, resetting the computer, or using the break key, the virus's own code would run instead of the typical routines, making it safe from user resetting the computer via commands or a key combination. The payload itself, which in this case was displaying text, would be called when the user attempted to save a file or load a file under the conditions that the computer was operating in the basic command prompt mode, the vertical retrace was 128 or higher, and that the time on the Jiffy clock, the C64 internal clock, had its seconds field between 2 and 4 seconds, making it very, very random. In terms of the virus part, copying itself, when a save or load function was performed by the user, it would check whether the file the user was saving was a basic program, and if it was, and was not already infected, it would embed itself within it before saving to disk. Otherwise, if the user was loading a file, it would go through the drive and find a program to embed itself within. Since the C64 had no overwritable memory other than floppy disks and RAM like a modern computer does with a hard drive or SSD, to get rid of the virus from the computer itself, all one had to do was turn off their C64 and turn it back on again. What do you know? Good advice after all. Oh, and also, throw away all potentially infected floppies to stop spread, or run a program that specifically searches for the virus and removes it from the floppies. This is just one of many viruses for the C64, but they all functioned in largely the same way. One interesting improvement, if you could call it that, on the concept is the frog virus, which installs its infection routine in programs that have been crunched by a type of program popular for the C64 known as a cruncher, which would make programs smaller and make them work faster and more efficiently. In particular, Cruel Cruncher. The result being, for this use case, that it would be impossible to detect the virus in a program without unpacking it first, but can still be gotten rid of by just turning the computer off and on again and just not risking it with that program anymore if you detected an infection. Well, anyways, thanks for watching. I hope you appreciated this more theoretical video, I suppose, more research-based, things like that. Let me know if you'd like to see that, and more gameplay vids are coming. Thanks for watching. Don't forget to hit that subscribe button and like button if you'd like to see more. Bye!